Well, hi there. Welcome to this video that related to kinematics in 2 dimensions. You probably just finished studying kinematics in 1 dimension, so we're going to just take it to a 2nd dimension. And for that, we're going to need to use some vector skills, which I hope you have. Simple things like adding vectors, finding components. That's pretty much all you're going to need to be able to work through these problems. And I'm going to show you a very general case of a problem in 2 dimensions. You're probably more familiar with specific cases such as projectile motion, that's actually an example of this, and circular motion of some kind. Orbiting motion, for example, is also kinematics in 2 dimensions. But we're going to look at a very general case, and I'll try to help you picture what's happening, because when you look at the math expressions, they can be a little mysterious, but I think when I show you what it looks like, it'll kind of make sense. So a lot of times you're just going to be given a couple of functions that describe the horizontal and vertical motion of an object, and they're happening simultaneously. Now in math class, you will call these parametric equations. We just tend not to use that term in physics, even though that's really what it is. So suppose we have something described this way. The horizontal position, or x as a function of time, might be 5t squared minus 6t plus 7. And at the same time, you have some motion in a perpendicular direction. Maybe that'll look vertical on drawing. Could be minus 15t plus 1. So what would this look like? Well, typically what we would do is we would plot this as y as a function of x. So we're not going to plot as a function of time. So what I did is just put it into my calculator, and you can see the display here actually forms a parabola. Now, what I did on my calculator is I looked at times even before 0. When I look at just time starting with 0, I think I can change that pretty quickly here. Then we just get the bottom half here. So that might be what it looks like if you were looking at something moving across the floor or across the ground. It would make a path like that. And the time, you don't really see the time here, but what I did is I just got an x and a y value at different times, and I plotted it along there. So if you put your calculator in parametric mode, it will probably do the same thing. So one of the first things I might recommend doing is finding out what the velocity functions and acceleration functions are. Because if you know how to work in 1 dimension, you can do the exact same thing in 2 dimensions. So what we have to do here, though, is still work in components. So the horizontal, or x component of the velocity, is just going to be dx dt, the derivative of the x position function with respect to time. So you take the derivative of that, and you're going to get 10t minus 6. And then similarly, the y component of the velocity, we would say, is dy dt, the derivative of the y position function with respect to time, and that's just minus 15. And if we do that again, we'll get the acceleration in each direction. So the horizontal is 10, and the vertical, because this is a constant, there is no vertical acceleration. So we've taken some derivatives there. Now you might be asked, well, what is the actual speed at a particular time? So if we look at that, let's just make up a time of 3 seconds. What is the speed at 3 seconds? What we have with these functions here is we have the ability to find out what the components of the velocity would be. But the speed is just the resultant, or the sum, of the 2 individual components of the velocities. So we now know how to find the horizontal velocity at 3 seconds. Just plug 3 into that. And that's going to get us 24 meters per second. That's 10 times 3 minus 6. And then the y component, Vy, is of course negative 15. That's a constant. And so how would we get the actual speed? Well, with a vector problem like this, I typically draw it. So we have a rightward 24 and a downward 15. And so I would represent something like this, 24 meters per second rightward, while also having 15 meters per second downward. And then let me draw a resultant in a different color. So that is the actual velocity vector. We would want to describe the angle that that makes, because when we're moving in something other than just a horizontal or vertical, it's nice to know what direction that is. So we would do Pythagorean theorem here to find the speed, and we would use an inverse trig function to find theta. I'm not going to show you that work because I think that geometry should be manageable for you. But this comes out 28.3 meters per second at 32 degrees below the positive x-axis. And then we might be asked, well, what is the acceleration at 3 seconds? And this is actually a little easier because if you look, we only have horizontal acceleration. We don't have any vertical, and it's also constant. So that's going to be just 10 meters per second squared towards positive x. And we could plug in any time that we would want to find out this kind of information. So these are very standard kinds of things that we would do with kinematics. I do want to show you one thing that sometimes causes some confusion. We sometimes like to write a single expression for the position as a function of time. And what throws people off is that we often use the symbol r for this. We can't really use x or y because it has both an x and a y. So this is just some point out in space. It could be above, below, left, right of the origin. And so that generic symbol r is what we often use. So the r vector in this case has an x component and a y component. And so all we would do is copy down the function for the x coordinate, that's 5t squared minus 6t plus 7, and then we put the little I hat symbol on there to show that that's the x component. And then we would add in our vertical, negative 15t plus 1, and put j hat. So that might be how we describe the position function. And then from there you would do everything the same way. I just want you to be able to see how we would extract the horizontal and the vertical information so that you could do the rest of this. So I think that's enough. I'll have additional videos on specifically projectile motion, circular motion, and things like that. Hopefully this gets you started. All right, good luck.